Hello everyone. Today we'll talk about a two-port DC-DC converter control variable optimizer tool. Let's first come, which has been developed by Writtik, Shubham, and under the guidance of Professor Mallik at Arizona State University. So let's get down to it. First, we'll talk about the circuit diagram. So here we can see that it's a typical CLLC DC-DC converter. On the primary side, we have the DC link DC voltage, that is VP, which is transferring power to the voltage to the bias source, which is VS, which is considered to be the forward power transfer. We have the full bridges consisting of devices S1 and S4 on the primary side, and then devices S5 to S8 on the secondary side. The CP and CS are the resonant capacitors on the primary and secondary respectively. The LP and LS could be the leakage integrated or integrated leakage or the of the transformer, or could be external leakages. Of the resonant tank. The LM is the magnetizing inductance, which is also taking part in the power transfer. And we are also considering the parasitics of the transformer, the parasitic capacitance of the transformer based on the three capacitor model, which is the CPS, which is the interwinding capacitance. CTP is the intra-winding capacitance, and CTS is the intra-winding capacitance on the secondary side. The previous CTP is the intra-winding capacitance on the primary side. And then we are also considering the winding resistances. So RTP is the primary side winding, RTS is the secondary side winding, and then there is a lumped resistance which is consisting of the ESR of the resonant capacitors and the device RDS-ons during conduction. So at that RDS-on value could be typically taken at around 100 degrees, 75 to 100 degrees Celsius, depending on the current rating required. Once we have talked about after we have talked about the circuit diagram, let's get to the converter specifications. So what this tool does is for a given voltage and power condition, and for the inputs of the semiconductor devices, it calculates the control variables required to achieve that particular voltage and power conversion. So for that, what we need to do is we need to define the port voltages. That is VP, we have defined it to be 600 volts. VS, we have defined it to be 28 volts. Power transfer. The required power transfer is defined to be 1800 watts. The turns ratio is selected to be 21 on the primary and 1 on the secondary. The port inductances, it's 10.5 microhenries on the primary side, 20 nanohenries on the secondary side. The port capacitances, 9.62 nanofarads on the primary side. And 5.079 microfarads on the secondary side. The magnetizing inductance LM is selected to be is around 70 microhenries, and the DC link capacitance values which define the output and the input ripple as considered are selected to be 10 microhenries and 100 microhenries on the primary and secondary side DC voltage side respectively. The harmonics that determines how much accurate do we want our result to be. So typically higher harmonics corresponds to a higher accuracy. However, there is also a computational time trade-off as well. So currently we have selected those harmonics to be 19, which seems to be a good trade-off between execution time as well as the accuracy. Then we have also considered the dead times on the primary and secondary side. So that is considered. So those are 40 nanoseconds on the primary and 10 nanoseconds on the secondary. The phase shift range. So in this particular case, we give certain for the given control variables, we define a certain ranges during which the optimizer selects does the search, and then based on the range. Phase and the frequency control variable range, it selects the optimal control variable at the output. So here we define the phase range between that particular maximum and minimum value. So here we've given it to be between we want the control variable set between 10 plus 10 to minus 10 degrees. Here positive phase shift determines positive phase shift is the phase shift. It could be considered where primary side is leading the secondary side, and negative phase shift is vice versa, where secondary side leads the primary side. So those values are between, we have defined the phase range between +10 and -10. The primary side phase shift, that is the intra-bridge phase shift, is can also be defined in terms of degrees. So that can also be mentioned. So currently we've selected it to be 0. The secondary side phase shift also can be defined like the intra-bridge phase shift. Typically, most of the times the intra-bridge phase shifts or the delta modulation is utilized at low power operation. But at the moment, we have kept it to be 0 for this particular demonstration. So once you've selected those ranges, we can select the optimization objective. Basis on optimization objective, we have three different objectives. One is the conduction loss minimization. So in this particular case, we try to minimize the normalized values of the IRMS square into the RDSons of the devices selected. Then second is the switching loss. Here in this particular case, we try to minimize the switching loss. So what happens is that once we give the certain requirements in terms of the voltage and power, then it calculates certain control variables by solving the mathematical model of the CLLC. And at the end of the mathematical model, there is a possibility that there are multiple control variables which are available for the user to select. Basis on the comparison between these control variables, one can select the control variable which can correspond to the best most optimal in terms of the conduction loss, most optimal in terms of semiconductor switching loss, or could be most optimal in terms of the total combined loss as well for the semiconductors. So as a result of that, we have defined these three optimization objectives by minimizing those three functions. So in this particular case, let's select the total semiconductor loss minimization objective function. And then before going into that, let's also talk about the switching device specification. So in this, because this is a simulation type which is advanced, here we are also able to define the device specifications from its data sheet. So first we define the RDSons of the primary and the secondary side devices. So that is 100 milliohms on the primary side. So typically, because this is a high voltage side, we try to go for like silicon carbide or silicon carbide type of device. So that is the reason it typically shows like a larger value of the RDSons. The secondary side is a low voltage, high current side. So typically that show like very low values of RDSons. The RGs, the RG, that is the gate resistance, can be also obtained from the datasheet. So that value is 5 ohms on the primary and 2 ohms on the secondary. We also need to define the QGD, that is the gate to drain charge requirement for the device. So that is 7 nanocoulombs in the primary and 2 nanocoulombs in the secondary. We also need to define the COS and the output capacitance, time-related output capacitance. That is 108 picofarads on the primary and 1700 picofarads on the secondary. And then further, we need to define the input capacitance of those devices, which can be obtained from the datasheet, and additionally the total gate charge requirement as well, which can be obtained from the datasheet as well. Further, there are other parameters which can help us determine model the switching loss function better. So those are the gate threshold voltage. Then the plateau voltage, the gate drive voltage, and the number of parallel devices, and the capacitor ESR, inductor winding resistance, and transformer winding resistance. Basically, the ESRs, capacitor ESR, inductor winding resistance, and transformer winding resistance are kind of lumped within those RTP and RTP values. And we also need to define the inter and the intra winding capacitances in order to improve the modeling accuracy of the converter. So once we do that, we can go on to the optimize button and then tell the optimizer tool to basically provide us the control variables with the most optimal values, which corresponds to the total semiconductor loss minimization. So here we see that it has given us the switching frequency of 575 kilohertz. The phase shift is at 0 degrees. The phase shift is -6 degrees, and the primary and secondary side intra-bridge phase shift is like 0 degrees, because anyways that range was anyways set to 0. So utilizing this control variables, then we can go forward, and basis on the values of the semiconductor devices, device parameters obtained from the data sheets, we can calculate the losses associated. So first of all, it shows the currents. So we see that the primary side current is 3.35 amps on the and and 70 amps on the secondary for that particular power level, voltage and power level, and then the switching instant value. So here minus, due to the direction of the current, as we can see, the negative here corresponds to typically would correspond to is a direction which typically would correspond to a partial or a full ZVS operation on the primary side, and a positive current on the secondary side would correspond to a partial or a full ZVS condition. So partial or full, that depends on the magnitude of the current, and then that also depends on the dead time selection, as well as the device output capacitance requirements. So that is not delved into in this particular work, but this particular current magnitudes or the current directions seem to be favoring the partial or the full ZVS operation for this particular operation. And then further we come down to the loss values. So in this particular case, we have the three different losses: the conduction loss, semi-switching loss, and the total loss. So all three of them can be further divided into primary side loss, secondary side loss, and the total loss. So the total loss, like this loss values help give the user the insight of the device selection. So for example, if my primary side is dominating, for example, if we do the analysis in terms of the pie chart, which can also be seen on the right side. So here we can see that almost 52% of the loss can be attributed to the to the second to the switching loss, right? So that is corresponding to the primary side. So that means that the primary side device which you have selected might not be the most optimal, or the switching frequency at which it operates is not might not be exactly optimal. So that is something that gives the user the insight when we use the control variable optimizer tool, that the device output capacitance needs to be studied, and then that value can be optimized further in order to increase the efficiency of the switch semiconductor loss efficiency of the converter itself. Yeah, and then we try to and then we also have the efficiency button, wherein apart from the apart from the core loss of the transformer, we try to model as accurately as possible the rest of the losses associated in the converter, which are dominant in the total loss analysis for a given converter. So now we can see that how the control variable optimizer tool helps us in selection of the devices, helps us in comparison of the devices as well, and then helps us in calculating the obtaining the control variables associated with each type of loss functions. So this is within the advanced simulation type. There is also another one which is called as the basic type. So in this particular case, we have removed the functionality for semiconductor loss input, semiconductor parameter inputs. This is something which is which is slightly easier to run as well as understand. So herein we just provide the basic requirements of the circuit, such as the voltages and the power requirements, the transformer turns ratios, the resonant tank parameters, and the ranges of the control variables. And on the basis of that, it calculates for a given optimization objective, it calculates the optimized control variables, and also as well as it calculates the RMS current and switching instant values. And then we have also, so the in this particular scenario, the loss values are obtained for a default values of the for the semiconductor devices. So those values can also be like we can look at those values which are mentioned in the in the optimizer tool notes in order to get a better understanding of it. And then this tool can also work for the forward as well as the reverse power transfer. So in the reverse power transfer, the power would flow from the VS to VP, which is critically important because currently almost all the DC-DC converters are being designed in such a way to enable the bidirectional power transfer capability. That is the reason the reverse power transfer is also very significant. So as a postscript, I would say that this tool is extremely powerful, especially for people working into resonant converters, which includes the CLLC, LLC, or CLL, or maybe even not even just the resonant converters, but even the other type of converters such as dual active bridge or PSFBs, or like basically anything which includes a transformer that could also be utilized. Those values could also be input in this particular tool, and the control variables can be obtained for the operation of the converter in order to obtain the required voltage and power levels. And then there is also the control variables which are obtained from. So one thing to note here is that this particular tool does not give the required waveforms. So the control variables which are obtained from this particular tool can be input to the can be used and then input to the waveform generator tool, or also called as the wave simulation tool, which is also developed by us. And that once we and then once those control variables are input there, then it generates the port voltages and the port currents, that is the the VPP, VSS, IP, and IS currents. That gives the user a better understanding of how exactly the control variables are generating the port currents, and then what is the like other critical phenomenon of those port waveforms, such as the RMS current values and the instantaneous values. So yeah, that brings me to the conclusion of this particular tool tutorial.